Okay, well, maybe we will get started. So, hello, my name is Jesse. I'm giving a talk today. I'm also the president of PAIN. So this is one of our academic events that we've been doing this year. I think this is the second actual talk that we've had. I think Flynn had the first one. We've had a few other events, and then this is the second talk, I believe. And this one is going to be on magnetic monopoles. So I'm guessing you're all here because you think magnetic monopoles are interesting in the fact that you've been told that they don't exist, right? So very often in your classes, maybe like second year electromag or something, they'll say Maxwell's equations tell you that there's no such thing as a magnetic monopole. So I'm going to explore that a little bit, and we'll see if that's the full truth or not. So to get started, what is a magnetic monopole, right? Let's actually talk about what they are before we can actually start describing them. So have we all seen a bar magnet before, right? It looks kind of like that. What's so special about a bar magnet? It has a north and a south, okay? So how can we make a monopole? Right, so what is a monopole? Anyone want to have a guess? Yeah. A magnet with a singular pole. It's like almost in the name, right? Monopole. So it's something that is either entirely all south or all north. Pretty simple. Okay, well, how do we actually make a monopole? So we get our bar magnet and we break it in half. And has anyone actually tried this? Yeah, what happens? Do we get a monopole when we break a bar magnet in half? No. So what happens? We just get two more magnets, right? Where we break it, another north and south pole appear. So why does that happen? Well, this bar magnet is actually made of even smaller little magnets, right? So when we're breaking it in half, we now have a smaller region of magnet. And we can keep breaking it in half over and over and over until we get down to the actual atoms that make up the magnet, but they're like a little magnet themselves. And you can go to the fundamental particles, and when you go down to like the smallest fundamental particle, they all have this dipole, magnetic dipole moment, right? So something with a north and a south. And obviously we can't break those small particles further apart to then create like a north and a south bit, all right? Okay, well, that's pretty different to electric charges, right? So we've all seen electric charges before. You have positive and negative charge, right? They look something like this. So you notice we have the positive charge on the left there, and it's got the field lines coming out of it. I'm sure you've seen a picture like that before. And on the right, we have a negative charge with all the field lines going in towards it, right? So we can have these separated positive and negative charges on their own. Magnets look a little bit different when you talk about the flux lines or the field lines around a magnet. So I'm sure you've done the little experiment before. You place a bar magnet down and get some iron filings around it, shake it a little bit, and it sort of forms this sort of shape on the left there, right? Have we all seen something like that before, right? So curiously, this situation here actually looks a little bit like two charges. So there's sort of this symmetry, this analogous structure between a north pole and a south pole close together like that, and a positive and a negative charge together like that. You can see the same sort of field lines, right? Except the one on the left for the magnet is magnetic field lines. The one on the right is obviously electric field lines. So, you know, why can't we just have a north and a south, you know, like this two charges situation, right? They're pretty much similar. You'd expect maybe some sort of symmetry of nature that allows you to construct the magnetic equivalent of charges. So let's actually talk a little bit about fields and flux. So here I have just a picture of a charge, and I have a whole bunch of little lines about it. So we're actually going to like describe this a little bit more carefully so we can actually do some powerful math with it. So we have a bunch of field lines coming out of this charge. So what does this actually mean? So these lines represent the flux density which basically just means the field strength, right? Big arrow means big field, right? You've seen that before, hopefully. Okay, maybe new terminology is flux density, okay? So what is flux? Well, it's just the amount of field going through a surface. So the idea is that flux density is flux per unit area. Then the flux is, the flux density times some area to get you flux back, right? So flux over area times area is just flux. Okay. So to find the flux, it's just the flux density times the area. So maybe let's compute some flux real quick. So if I get a straight line like this, well, how can we actually compute the flux or the amount of field lines or the flow going through this shape? So I've drawn a little bit of a rectangle. You guys, I don't have to go and do geometry. I can skip a little bit and talk about integration. So what we can do, so how do we actually calculate the amount of flux going through this surface? Well, we can zoom in on this surface and break it up into little tiny chunks. So that pink arrow there is like the area vector. So it's normal to our surface. So if we have an area vector pointing straight up, and if we have, well, for example, if we had a blue arrow perpendicular to that pink line, to that pink vector, that pink arrow, if they're perpendicular, then obviously there's nothing flowing through that surface, right? So this pink vector, when you take the scalar product or the dot product with one of the blue vectors, it tells you how much is traveling through at a particular point. All right, are we convinced by that? So it's just a way of measuring. The magnitude of the big pink vector will be equal to the area of that shape. When you break it down into those smaller chunks, then it gets a little bit more complicated. Yeah. Okay, so then we can break it up into all these little chunks of length or area dA. And when we have little chunks, we can integrate over it, right? So to find the flux, it's E, the field, dotted with dA, which is the little area chunk. So those are the two vectors, the electric strength vector and my area vector, my little area vector. You can see we're integrating over A, which is that whole pink shape. Right? That gives us the flux. Usually we work with closed surfaces though. So this was just an open surface. It is useful, but more useful is something like a closed surface like this. So this is why we express it in this sort of formalism, because now we have an area vector that actually points in a different direction depending on where you are on this surface, okay? But it's the same equation, right? It's just E dot dA integrated over that surface. And you can see I put a little circle next to my integral there, right? And that just means it's a closed surface now. So we're going all the way around this circle. And so it's a closed shape. Like mathematically, it doesn't mean anything different. It's just so you recognize it's closed. All right. Now we actually have a really cool math theorem about some integral like this. And it's actually equal to some charge density over volume. So the idea is that the amount of flux passing through a surface is equal to the amount of field, to the amount of charge contained in a volume, right? It should be fairly intuitive sounding, right? If our charge creates a flow, well, the amount flowing out is going to be, the amount flowing out through an area is going to be equal to the amount actually enclosed in that volume, the amount of charge that's generating the flow. Okay, so this is Gauss's law, right? And specifically for this here, it's Gauss's law for electricity, right? So Gauss's law is just a general, Gauss's theorem, Gauss's law, just a general case, but we're specifically looking at electricity here. So then we have Maxwell's equations. So hopefully the first one you can sort of recognize as our little friend here. So this before was just an integral over this 1D sort of space, right? This 2D surface, this sort of flat space. When we go to 3 dimensions, we do an extra integral to encapsulate the one on, so the left-hand side of the first equation there is over some 2D surface. So like the shell of a sphere, for example, and the right-hand side, there's 3 integrals. So it's a 3D volume. So the volume of a sphere, for example, right? The second equation is pretty much the same, except it's for the magnetic field. So these are our laws of electromagnetism. Third one, not as important, right? It's to do with the curl, basically, or not the curl yet, but well, I'll add the captions in. So the first one, yeah, flux through a surface is equal to the charge enclosed by the surface. And this one is the field parallel to a loop is equal to the amount of field inside the loop. Yeah, equal to the amount the field inside the loop is changing. So there's a rate of change there. So when we change the strength of our field, it makes some of our field parallel to our surface. Sounds complicated, and that's fine. Basically, the idea is, where do fields come from, right? And these equations describe how we get fields. So the first two tell us we can get fields from charges, and the second two tell us we can get fields from changes of other fields. So a changing magnetic field for the third equation creates an electric field, and for the last equation, a changing electric field makes a magnetic field. Okay, so these ones are really ugly. We never use them like this, right? Notice how there's a little a and a little c on all of these. This means you have to pick a surface or pick some closed curve. We prefer to write them like this, which looks much nicer, but also maybe you guys don't know what those symbols are. So basically, we're replacing the integral with a differential operator and getting the same sort of equation. So instead of looking at the flux through the surface, now we're looking at the divergence, right? Which is just literally the amount of flux coming out of a point or out of an enclosed region, right? So now we're explicitly working with, at a point, how much field is coming out of that point, rather than going through an entire surface and looking at how much field is coming out of that surface. So it's at a point locally rather than globally, I suppose. Okay. And then the second two change, the curl is equal to the amount of the field inside. The curl is equal to the amount of the field is changing. Sorry. All right. So what is curl? It's pretty much what it sounds like, right? If I have an object in a field, how much does it curl my object or twist my object, right? And a lot of the time we don't actually even worry about these because for any conservative process or any energy conserving process, these curls are equal to 0. So a lot of time we don't even worry about them. It's only if we have changing fields or we're putting more energy into our system or something like that. So the important thing to note though, is that now in this formalism, these equations are now independent of our choice of surface. So we don't have to worry about integrating over a surface, right? We can just look at these derivative operators acting on our fields. We don't really need to understand too much about how they work, just that they do. So we only care about these two for this talk, right? So these are saying that we create field by having a charge density, right? So the first one says that the divergence of the electric field is equal to the electric charge density, right? Okay, yeah, so I have charges, it makes a field. The magnetic one says our magnetic fields have no divergence, okay? So that means we can't create a net amount of field, okay? So we have nabla or del or whatever you want to call it, dot B equal to 0. So it says, basically this means because it's independent of choice of surface, it holds for all surfaces. So through any closed surface, the amount of flux in cancels with the amount of flux out. So there's a net 0 flux. So what does that mean? So remember if we had, well, I'll get to that. So what does that look like? If I draw some surface around my magnet like this, if you look really closely at the arrows and count and look at the size of them and the direction of them and add them all up with the amount going through this surface, it will be equal to 0. So I can go through and look at the ones at the bottom coming out, the ones at the side just touching, the ones at the top going in. It will all add up to 0 over any surface. And by any surface, I mean literally any surface. So we can have like one on the left here, where it's a nice round surface around the whole magnet. I can draw my surface like the one in the middle, where it's around just one of the poles. Maybe not, actually. I think I drew that. Well, actually, that's not quite true. So the one in the middle, you can see it's only around one of the norths. So the field lines are coming out, right? So in that case, there would be a net amount of charge. But if I have my whole magnet enclosed, so we can't actually draw a surface. We can't construct the surface like the one in the middle in reality, right? Because that would require chopping through our bar magnet. But the one on the right here, you can see that when we have no charge enclosed, again, there's a net zero. So if I look at these little arrows coming out of the one on the right and look at the little tiny arrows going in, they will add up to zero. Okay? But we can't construct the one in the middle physically, right? Because it would be chopping through our magnet, right? And we can't have the magnet by itself like that. Okay? So what does this mean? It means we can't have a north pole like this, right? With the arrows just sort of coming out. So sort of like what we had here, just with the arrows coming out. We can't get this north pole by itself. We can't get this south pole by itself. So it's prohibited by this condition, nabla.b equal to 0, right? So these would be non-zero, right? You can see how there's a net amount coming out. Okay. So why can't we just have it not equal to 0? Like, why do we have to have it equal to 0? It sounds like a really arbitrary thing that we've put there, right? Why can't we have some magnetic charge density? Well, turns out that's not even a physics thing now, but we'll get to that. So how do we actually define a magnetic field to start with? What is a magnetic field? What is an electric field? So it turns out magnetic fields and electric fields are actually related to something called a scalar potential and a vector potential. We don't really care too much about the scalar potential today, but the vector potential is really important. So the same way you can describe like a gravitational field in terms of, well, a gravitational field, you can also describe it as the gradient of a gravitational potential, right? So you've all heard gravitational potential energy before. You know that you've got like mgh or whatever. You can do something, some mathematical operation to construct your field back out of your potential. For electromagnetism, it's a little bit more complicated because we're now dealing with vector fields, right? And it gets a little bit cooked, okay? So our potential needs to be a vector. Okay, so then our magnetic field is described as the curl of this A vector, right? And our electric field is described like this. So these are some ugly looking equations, hopefully not too ugly, but because we'll have some uglier ones later. But the idea is that we get the magnetic field as the curl of this A field. That's the A potential, the vector potential. And that's the important thing. Okay, well, we actually have a theorem in vector calculus that says the divergence of a curl of any vector field, maybe I should put an asterisk next to that, of a vector field is equal to 0. Okay, well, B is just the curl of our vector potential. So that means the divergence of B is 0. So it's not even a physics thing anymore. It's a mathematical law that we can't have a magnetic divergence, okay? So not even a physics thing, it's a mathematical law. So conclusion, magnetic monopoles don't exist. Thanks for watching. All right, okay. Maybe we should be a bit more careful, right? I sort of waved my hands a little bit there when I introduced the vector potential. Maybe let's go a little bit more slowly and see if I did everything quite right. Okay, let's be a bit more careful. So our vector potential is really, really important here. So let's look again at our B field and our E fields. So there's something I didn't actually tell you about our vector potential before. Well, how do we actually define our vector potential? Yeah, turns out there's no one good way to define it. So this is like a really important concept in physics, and it's the idea of gauge symmetry and gauge invariance. So actually, if we create a new vector potential A, where we've just added on the derivative basically of some other function, right? Of any function that you want to come up with, you take the derivative of it, add to our A, get a new A. We know that the curl of a gradient is equal to 0. That's a mathematical law. So then we can show that the curl of this new vector A prime, we can do a bunch of math. We can actually show that it's equal to the curl of A, which is equal to our magnetic field, right? So this new A prime that we've constructed just by adding the gradient of some function, it gives us the same magnetic field back. We can do the same for the electric field as well. We can take the derivative of A prime, and basically we get the same electric field back. Okay, so we can just arbitrarily change our vector potential A by some function. Kind of bizarre. So this is actually something really, really important. We made this change and we got exactly the same B and E. Okay, this might seem like really, really arbitrary and not very important, but it's actually really, really, really useful and important in a lot of high-level theoretical physics. So this brings us to the idea of gauge theories. So our magnetic potential is only defined up to the gradient of some scalar function, right? So we have this choice or this degree of freedom or this symmetry by modifying this function f, right? We can change between different functions f and get a physically equivalent description of nature. So there's sort of this built-in redundancy in our description, right? So our theory has a built-in degree of redundancy. So we can choose whatever f we want to describe our potential. It won't affect the physics, right? It's got this symmetry. You saw, we chuck in our vector potential, right? Doesn't matter what this f is. We do our operations to get our E fields and our B fields. We use a different vector potential. We get the same E and B fields, right? It doesn't matter, right? There's this symmetry there. So yeah, very, very important. We have what we call a gauge symmetry, right? We can arbitrarily change our function. So this, a lot of people have a lot of trouble grasping this concept because it is a little bit complicated, the idea of a gauge theory. But it's not actually that unfamiliar to stuff you've seen in physics before, right? So you've worked with gravitational potential energy, right? You know, you drop a ball, it falls to the ground, right? I'm sure you've all done that at some point. Where do we draw the line of zero potential energy? It's arbitrary, right? We can draw it along the ground and say, this is our zero of our energy. If I hold an apple up and I drop it from that point, we could say we started with zero gravitational potential energy, and then as the apple fell, it gets negative gravitational potential energy. That 0 point is arbitrary, right? So we have this degree of arbitrariness in our description of the physics, right? It doesn't matter where we draw this zero potential line. Same thing with electromagnetism, right? When we talk about voltages, where's our 0 volts? Where's our 1 volt? It doesn't really matter. You know, if I can call this 0 volts here, it just means that it's going to be 1 volt here, -1 there. If I call this over here 0, it's going to be +1 and +2. It doesn't matter. You know, you've got some freedom on how you want to describe your system. Actually, interestingly enough, this is also like useful in finance. You can actually use this theoretical physics stuff in finance as well. When you talk about like exchange rates, I can double the face value of my currency, double all my pay for my employees, double everyone's money in their bank account, right? You double the price of everything, you double how much you're paying everyone, nothing changes, right? There's a scale invariance, you could say, or something similar to that. So this is actually a really common phenomenon. So yeah, I gave you that analog, right? Our choice of 0 for the potential energy doesn't affect the physics. It's an equivalent description. Okay, well, let's see if we can exploit this symmetry to find some monopoles. Okay, so buckle up because this is where we actually get to a little bit of math. So normally electric fields from a point charge look like this. Hopefully you've seen that before. We've got Q, our electric charge. Basically it's proportional to 1 on R squared. You know, I'm sure you've seen the R squared law, inverse R squared law. Okay, so we should probably try to construct a magnetic field that looks similar, right? So let's create an A that gives us a similar looking magnetic field, because this is the electric field for a point charge. If we can come up with something similar for magnetism, that means we found a vector potential that gives us a magnetic point charge which is a monopole, right? That's exactly what we want. Okay, so the easiest way to do this is to use 3D spherical coordinates. So I imagine that maybe not everyone has seen spherical coordinates before. So I've attached a handy little diagram to the right there, and I'll just sort of explain. So normally when you have 3D space, you probably want to look at X, Y, Z coordinates. But for systems that have a lot of radial symmetry, you want to use radial sort of coordinates, so spherical coordinates or polar coordinates or something like that. So the first coordinate is R. That's literally, you draw a line from the origin to your point. How far is it? Okay, your radius. Your theta and your phi is sort of like your angles. What are they called? Like azimuthal and elevation or something like that. So it just tells you basically how to tilt your vector to sort of point at your point in 3D space, right? The specifics aren't too much. In fact, we're only going to be working with a vector potential with a phi component, no theta, no r, okay? And actually, this diagram isn't great because I've actually swapped the theta and the phi in my calculations. So just keep that in mind. Okay, so let's just have a look at this first sort of equation here, this an phi, okay? I've just constructed an arbitrary vector potential like that, just some function, right? Okay, if I take the curl of that function, so I'm taking the curl of my an, right? I get something that looks like g on 4 pi r squared from this equation. So I've constructed this equation explicitly to get this out. Okay, well, what does this look like? If g is my magnetic charge instead of my q, this looks exactly like a magnetic monopole, right? This is completely analogous to an electric one, right? This is the same equation, just with a g instead of a q. So we've done it. We found it, right? Okay, all right. Hang on. There might have been something wrong with that, right? So yeah, I constructed this function. Yeah, I took the curl, but we have something like this, a magnetic field in the radial direction, analogous to our electric field we had before. And if you take the divergence of this, it's not zero. All right, I'm not going to show you the math, but it's not zero, right? The same way when we take the divergence of the electric field, we know it's not zero, it's the charge density. So something funky's happened. I said that we can construct some gauge field, some gauge vector, rather. Some vector potential, that's a better word. Some vector potential. I've taken the curl, I've gotten a field, and the field says there's monopoles. Bizarre, right? This is a curl, right? And I said before, it's a mathematical theorem that the divergence of a curl of a vector function or a vector potential is zero, right? Mathematically, this shouldn't be allowed. So what happened? What happened? How can this be allowed? Okay, let's have another look at this. Can we see a potential culprit that may make this act a little bit funky? So what happens when theta is equal to 0? We get cos of theta is 1. So we get 1 minus 1, which is 0. And we get sine of theta, which is 0. We get 0 divided by 0. Uh-oh. Well, actually, that's not a problem. What is a problem is when theta is equal to pi. Now we don't get a 0 over 0. Turns out that 0 over 0 actually cancels out nicely. But when we take theta equal to pi, well, that cos is not canceling out that 1 anymore, right? That sine of theta, sine of pi, is 0 as well. So now we get something that's undefined, not just at one point, but a whole line along theta equal to pi, right? So that's why I gave it a little n, because it only works when you're up north, okay? Well, that's not good. That's not any good, right? Because, yeah, I've constructed this gauge, this vector potential, but it's undefined in, an entire countable region of space. That can't be good, right? All right. Okay, let's try again. Let's try again. So let's try to fix it up when theta is equal to pi. Okay, let's try this one instead. We got a south there. Okay, so now when theta is equal to pi, this one works. Okay, I know what you're thinking. We still get the same issue, right? When theta is equal to pi, sine of pi is equal to 0. But what's cos of pi? Did I miss a sign? No, the sign is right. What's cos of pi? -1. Oh, well, now we get 0 divided by 0 and everything's great. That's fine. That's fine. It actually is well defined at that point, I promise you. But now what happens when theta is equal to 0? Well, cos of 0 is 1. Sine of 0 is 0. Now we get division by 0 again.
Is it like not when r equals 0? Or would it be like heading to the point when
It's fine. It's fine. Well, what's theta when r is equal to 0? Yeah, I think technically you're allowed to have it undefined at 1 point, and then it's not an issue. But we have it undefined at a whole lot more than 1 points. In fact, you know, we have an uncountable number of points where it's undefined, okay? Which is a bit of an issue. Or is it? Okay, so this is undefined when theta is equal to 0. Okay, well, that's not great. I've cooked up 2 different vector potentials. And when I take the curl of this one, it also gives me the magnetic field we want, right? But it's still not defined. So again, we get the same magnetic field through this vector potential. Okay? So we have 2 different vector potentials describing 2 different situations when we're living in the north half and when we're living in the south half. And they only work in those 2 areas, right? Okay. Now, if we have a close look at these functions, shouldn't these be the same? They're physically equivalent, right? They gave us the same magnetic field, right? We took the curl and it gave us the same field each time. They both have singularities though, which is not good, right? So now let's remember that A has a gauge degree of freedom. So remember, we could add in that scalar function before, right? And we could arbitrarily change between A's. Well, what if I made some sort of transformation, right? So remember, these are physically equivalent. We can change by the gradient of some function. Okay. We actually have that AN is equal to AS plus the gradient of some function. I've written it a bit funny there. That's because I've actually taken the gradient of F. F was only a function of phi, so the radial components and the, well, I haven't shown you F yet actually, but the radial components and the theta components cancel out. So we just get some component like that. And if we actually expand it out, you'll actually see that you get these, right? We can construct AN from AS by adding the gradient of some function where F is this, right? So F is only a function of phi. So the derivatives in terms of theta and r, you know, remember our 3 coordinates, r, theta, and phi. The other ones are equal to 0. So we just get this ugly looking transformation here, right, on this F, where we've defined F as g phi over 2 pi. Okay, great. So we've related our 2 different gauge, 2 different vector potentials together, right? So they're physically equivalent. We've just proven that they're physically equivalent. Cool. So indeed, AN, the north one, is equal to A south plus the gradient of some function F. So that's good, right? We've constructed this field, right? And they're just related by some transformation. So who cares? You know, the description for AN works when we're in the top. AS works when we're in the bottom. So we just pick whichever one we want, right? When we're in that particular region of space. I know that sounds a bit hand wavy. It's like, how can that be true? But remember, these describe physically equivalent situations. So the singularities that we have can be sort of explained away by just shifting to a different function that describes the same system. And this is something we do actually all the time, right? In high level theoretical physics. So we do actually precisely this same sort of thing, right? when we look at stuff like electromagnetism. A lot of the times it's easier to describe with these gauge functions, right? Where we have this extra degree of freedom. But remember, this degree of freedom isn't physical. So often when we actually construct our theory, we have to get rid of some degrees of freedom. So for example, you guys have heard of photons before, right? Light. So how many polarizations does light have? Well, okay, how many polarization vectors in a basis for a polarization of light? A number bigger than one, maybe? Two, right? Have you seen like up and down polarized and left and right polarized? That's a basis, right? You can describe any polarization using that. You can look at circular and I guess opposite circular. I was gonna say anti-circular, clockwise and anti-clockwise, right? That's a basis. You can describe any polarization as a linear combination of those two polarizations. Well, when we actually construct the quantum version of electromagnetism, we actually work with a photon that has 4 different polarizations, right? So we work with something called longitudinal polarization. I'm sure you've heard of that before. Like a spring or a slinky, we can shoot a longitudinal wave across, right? I was going to say, no, I can't say that. So you've seen that before. And I'm sure they've made a point to tell you that there's no such thing as longitudinally polarized light. Cool. There's also time-like polarized light, which God knows what that means, all right? But we include these redundant parts of our description in our theory and remove them later because it helps us describe. So this is, again, just a bit of context about this whole gauge stuff, right? Because it sounds like I've just been very hand-wavy with the math and just thrown math around everywhere. But it's actually something that's used very rigorously in a lot of different theories. Okay, so great. We've got this AN, we've got this AS, we've related them, and we can construct our monopole field. Great, this is great. Can anyone see an issue? Oops, maybe, can anyone see an issue? So, I'm not going to go back that far. This F here is described in terms of phi. What happens when phi is equal to 0? Or more importantly, what happens when phi is equal to 2 pi? Yeah, but when phi equals 0 and when phi equals 2 pi, that's like a full rotation, right? Your system should be back in the same state. Your function should be the same, right? Because you've went from being 0 elevation to 2 pi elevation, which is wrapped all the way back around to where you started, right? But this function f is not periodic, right? So f is not single valued, right? So phi equals 0 is equal to 0 for f. F of phi equals 2 pi is equal to g. Okay? But obviously 0 and 2 pi are the same angle, right? In our coordinate system, because it's polar coordinates. The angles wrap back around on themselves. Okay, well, that's not great. So I've come up with this whole big description. I've shown you the fields are there. I've come up with this function, but the problem is our function f is ambiguously defined, right? So if I want to describe my position in space, with this phi, if I have something like, for example, if I have my point particle directly above the z-axis, or along the z-axis, directly above the origin, do I describe that as phi equals 0 or phi equals 2 pi or phi equals 4 pi, right? What's my f there? We don't know. Bit of an issue. Actually, it's not as much of an issue as you think, all right? This just means we have to be a little bit clever. So remember, these vector potentials, they're not really describing the real system, right? They're sort of living in this math land with some arbitrary degrees of freedom. When we actually describe reality, a lot of those extra things cancel out. So like the photon example I gave you, when we're working with the quantum version of electricity and light, we work with a 4-component, right? A 4 different polarization photon. Obviously, we don't have that in real life. It's just a 2-component. So when we actually translate to reality, we lose some of the stuff. So can we lose the not single valuedness of the f function? Hopefully, right? Because otherwise we've just wasted all our time. Okay. Let's consider the wave function of an electrically charged particle in quantum mechanics. So if you haven't done any quantum mechanics, this will be a little bit hand wavy. So basically the wave function contains all the information about your particle, where it is, where it's going, loosely speaking. Okay. So let's say we have an electrically charged particle in quantum mechanics. What happens if we have a magnetic monopole and move an electric charge in a circle, a closed loop around our monopole? What effect will the monopole have on our charge? Now, that's a bit of a complicated question. Basically, we have some gauge transformation acting on this particle, and it's some ugly looking exponential like this. What does that mean? I have no idea. That looks really terrible. So the important thing is, right, these wave functions are a complex number. We can see e to the I something. So all that's happening is we're rotating our wave function by phase. Okay? So, and this phase is proportional to our closed loop integral over our vector potential A. Okay? So remember, we just had our vector potential A before. We're integrating around it. You don't have to worry too much where this equation comes from, but that's a fact. When you integrate over, when you move a particle around in a magnetic field, it accrues some phase, right? And the phase it accrues is related to this vector potential. Yeah. Oh, sorry, E is just the electric charge. Yeah, sorry, I meant to mention that. Okay, so what's happening? We're just rotating our function, our phi, sorry, our psi, our wave function by some phase. And if you know anything about quantum mechanics, you know that when we have a phase, it doesn't matter. The phase cancels out anyway, most of the time. So yeah, we get some wave function looking like this. Okay, so how do we make sure that this wave function is completely unchanged? How do we keep the phase intact? Well, that just means that we have to have something like this whole constant inside the exponential is just equal to 2 pi I, right? Because that's one full rotation on the complex plane, which brings our wave function back to the original phase it had originally. Okay, so how do we make it do a full rotation? Well, it's unchanged as long as this bit inside the phase there is equal to 2 pi n. Okay, so as long as it's a full 360 degree or a 2 pi rotation on the complex plane, it's going to bring your function back to its original state. Okay, so this actually, we can rearrange this equation here, this bottom one, with the e's and the g's and the h bars and the 2 pi's, and this becomes the Dirac quantization condition. Okay, so if we are to have a monopole, the electric charge multiplied by the magnetic charge has to be a multiple of 2 pi h bar, an integer multiple. So if our electric charge is quantized, any magnetic charges we see will also be quantized. And if magnetic charges exist, this means that the electric charge is also quantized. So actually finding a magnetic charge would be really, really important because it would tell you that, yeah, electric charges are quantized, right? So yeah, this gives us 2 implications. If magnetic monopoles exist, the electric charge is quantized. So and we've observed, from what we observed, the electric charge is quantized, but we don't know why. So this would give us an explanation, right? For this electromagnetism stuff to be consistent. If we had a magnetic monopole, we move the charge around. For quantum mechanics to be consistent, we need quantized charges. Okay, so what we've observed at the moment is that the charge should be quantized if, like it is, if we have monopoles exist. The other implication is if we find an electric particle with irrational multiples of charge, then monopoles don't exist. Okay, So what you've seen at the moment, right, is if I have an electron with 1 unit of electric charge, I can have 2 electrons with 2 units of electric charge, right? Ignoring quarks and stuff, that would be the smaller charge, but still they're integer multiples. So if I found something with root 2e of a charge, then there's no way to construct an integer multiple of that, right? Because it's an irrational number, right? You can't find some smaller amount of charge and just say, oh, they're both multiples of this, because it's irrational. So if we observe some irrational amount of charge, so if someone finds some particle with, root 2 times the charge of an electron, then we know that there's no such thing as monopoles, because it'll violate this condition, right? But we've never seen something with a root 2 or any irrational number amount of charge. Okay, so we haven't ruled out the existence of monopoles there. Okay, so therefore, nothing here forbids the existence of monopoles. Okay, so we haven't seen them yet, but there's nothing mathematically that rules them out. All right, I know I did a lot of hand wavy stuff with the vector potentials, but I promise you that's actually well defined, right? Once we went through it, right? Well, we showed that it's well defined as long as we have this condition. Okay, so we can also generalize this to dyons. So a dyon is a particle that has both electric and magnetic charge, right? And this gives us some formulas like this. So basically, if we have a different monopoles, different electric charges, they have to have a difference that's a 2 pi on h bar times an integer amount. So we can have like different species of electric charges as long as they're related in this particular way. Different types of monopoles and different types of electric charges. Okay, this is just a little bit of extra. Okay, so other monopoles. So this was just one way of constructing monopoles. Apologies if you thought it was a bit basic. Turns out you need a lot of heavy machinery to construct this stuff, right? So the stuff that I was talking about today, it's actually taken a little bit out of a master's course on gauge theories, just like a very, like the first few pages out of like a 600-page set of notes. So there's a lot of other ways to construct monopoles as well. And there's a lot of other places we can look for monopoles. So everything we were talking about today was all in free space, right? So just like we have electrons in free space and stuff like that. There's also other types of particles that only exist in materials, right? So if I like tap this desk, right, vibrations go through it, right? That's how sound travels. So it turns out we can actually quantize sound as well into particles called phonons. And these phonons, obviously, they only exist in a material. They can't exist out in free space because they're sound, the old saying, no one can hear you scream in space or something like that. Okay, so here's just a list of a few places where we can actually have monopoles arise. And if there's enough interest in these, I can actually maybe do another talk at a later date on where they can arise. So one place we can have monopoles come out is from topology. So by modifying the topology of our system. So for example, on a torus, right? If our universe was a torus, it wouldn't be that far-fetched to have monopoles. Okay, I think they exist quite naturally, including if we have a wormhole, right? If I join a point in space here to a point in space somewhere else, we can have non-trivial flux or something, and essentially that gives us a monopole outside of the wormhole, right? So whenever we modify the topology or the number of holes in the space, then that can change whether monopoles are possible or not. So I believe on a torus, it's quite natural. Can arise in materials. So the same way I spoke about phonons existing, we can actually get monopoles in materials. And I believe people have been looking for them. I don't know if they've actually found them or whether they've thought they've almost found them potentially as candidates. So I think in materials, it's a bit easier because you can have something that looks like a monopole and have like the poles sort of travel in either direction. And essentially you've got isolated poles. I believe in condensed matter stuff, when you're looking at, I know a research group that I was involved with was looking at some sort of lattice with high spin and low spin sites on the lattice, you can do something funky and get something with potentially monopoles. So those are the two main places that you can get them. So this leads to some further topics for investigation, right? So we have the Aronov-Bohm effect. So this is related to what I was talking about with having an electric charge or a monopole in space and moving a charge around it. This is actually more related to topology. So it's the same idea of moving a charge around in space. So what if I have a space with a hole in it, right? And I move my electric charge around that hole, what happens, right? Turns out if you have a hole in space, or rather than a hole, maybe an infinite line missing in space. So I put like a really big rod through space that you can't go through. You would think it'd be like roughly the same as just moving around just normal empty space, right? But it turns out when you enclose that hole with a loop in your motion of your charge, turns out you actually get a phase factor relating to the gauge potential as well. And this is actually observed. You can get like quantum interference effects just from the topology of a space, which is something I found quite fascinating. But again, related to that idea of your vector potential. Half integer spin bosons and integer spin fermions. So you can do some cool stuff with your monopoles. I don't know too much of the details on this, but you can actually construct bosons with half integer spins and fermions with integer spins. So if you know what those words mean, you might go, wow, that's kind of weird. If you don't, then when you finally learn what those words mean, you'll go, wow, that's kind of weird. We can also look at the Maxwell action and look at topological terms, specifically the theta term. So whenever we describe like some quantum field theory, we describe it in terms of its action, which is just the integral of the Lagrangian, which is the difference between kinetic and potential energy. So take the difference between kinetic and potential, integrate it over all the space, right? We can add an extra term to that called the theta term. When we take the equations of motion for our system, the theta term just disappears and we get our physics the same, right? And that's something we see all the time. But turns out it's not actually the same. We can get some interesting properties from this theta term. So particularly topological insulators. So I think depending on what this theta value is, you can actually get some really interesting effects. So something called the topological magnetoelectric effect. I believe it's when you run an electric field into a surface, it generates a magnetic field inside the material. And if I have a magnetic field outside the surface, it generates an electric field inside the surface. And I think this can be modeled with monopoles as well. And the last thing I believe is mirage monopoles. So these are monopoles inside materials. I think this is again related to the theta term potentially. So the idea is if we have maybe electron outside of some metal, if the metal has a particular value for its theta term, then it will actually create a mirror magnetic monopole on the other side. So anyone who's done third-year fields and has maybe looked at what do they call it? The mirror method of constructing a field or something. So the idea is you want to find the field inside a material, you place a charge outside, you construct a false charge on the inside to look at how the field interacts with the surface to satisfy the boundary conditions. You can get something similar. So in that case, we'd say there'd be an imaginary mirage electron or something. In this case, with this theta term, with this topological magnetoelectric effect, it's like having a magnetic monopole inside the material, the way it generates a charge, a field, sorry. Cool. Okay. And the last thing is the Witten effect. Basically, it's to do with monopoles gaining an electric charge, right? And I think that's, again, to do with the theta term as well, right? So I think, yeah, a monopole inside a region with a non-zero theta term it gives it a charge or something like that. Okay, cool. That is everything I wanted to talk about. Cool. I hope you enjoyed that. Oh, yep.